Now we're going to talk about the geometric distribution. All right, so this is similar to the binomial distribution. Let's talk about what the situation is. All right, so we still have a situation where P is the probability of a success. Okay. And that's in each trial. So it's the same where I have a fixed probability of success for each trial. All right. The difference is in the number of trials and what X is. So X is not the number of successes out of N trials. X is the trial number of the first success. All right, so what's the difference? All right, so if I had, flip a coin, then I do that over and over, repeatedly. P probability of heads 1/2, or tails, whatever you want. All right, so P is 1/2. All right, so if I say, okay, flip 10 times and count the number of heads. That is a binomial distribution where N is 10 and P is 1/2. All right. But if instead I flip until I get a head, and here an X is the number of flips. All right, well, in this situation, I have a geometric distribution with parameter 1/2. So there's no N because it's not a fixed number of trials. As soon as I get a head, I'm done. So if I flip a head on the first trial, then I only do one trial and I'm done. But if I get the tail, the next one's the tail, and the next one's the tail, and so eventually, on the 10th flip, I happen to get my first head, the next is 10. All right, so that's the geometric distribution. All right, so let's do our definition. All right, definition. So we say that random variable X has the geometric distribution with parameter P if, all right, so here's what has to happen. There's an unspecified number of trials. All right, so there's no N here. There's no flip a coin 10 times or flip a coin 50 times or whatever. There's an unspecified number of trials. All right, we still have 2 outcomes in each trial. That's either a success or a failure. And X equals the number of trials until the first success. That's the number of trials of the first success. I might say that. Still, our outcomes are independent. Flipping a coin repeatedly, each flip is independent because the probability is a half every time. So no matter what happens in the first flip, it's not going to affect the probability of the next flip. We talked about last time when we were talking about binomial distribution, an example of something that's dependent or not independent would be if I was picking the card and I didn't put the card back in shuffle. So if I just pick a card and let's say I'm going to do it until I get the ace of spades, and then I flip the first one and it's not an ace of spades, and the next one. But basically the probability of an ace of spades for the first time, for the first card, is 1 over 52. There's 52 cards. But once I pick that card and I throw that aside, discard that card, now there's only 51 cards. So the probability is now 1 over 51. And then after that, 1 over 50, etc. Those are not independent. Okay. And the probability of a success, we call that little p. And then the probability of a failure, we call that q. Little q. And this equals 1 minus p. All right, so success and failure are complements of each other, so they have to add up to 1. All right. All right, let's talk about a rule. All right. The probability distribution for the geometric distribution is the following. Okay. So let's think about it. All right, so let's say that I want to find out what's the probability that the first, let's see down here, probability of the first success is on the 8th trial. All right, in order for that to happen, I have to get a failure, I have to get 7 failures, and then a success. Right? Now these are independent. So the probability, so once I get, so this is the probability of a failure, that's Q. P is the probability of success. This guy has probability P. But since these are independent and my probabilities are fixed, then this guy also has probability Q. And all the way down, this one has Q. Well, I guess the probability of a failure in each trial is Q. The probability of success in each trial is P. Right? So since these are independent, and I want to know the probability of a failure and a failure and a failure, all right, we're going to use the multiplication rule. That says the probability of A and B is the probability of A times the probability of B given A, which is, so this is going to be probably, this is going to be Q times Q times Q times Q times Q times Q. Let's see, 1, 2, 3, 4, 1, 2, Q, and then P, which is Q to the 7 times P. Right. So the way we write this, so that's going to be, that type of pattern is going to exist. All right. So this is, by the way, this is P of 8. Right. So P of X, and for whatever reason, they always put the P first, but all right. Probably that we have that our first success is on the X trial is going to be P times Q to the X minus 1. So this is P, this is the same as P times Q to the 7. All right. So P, we're going to have one success, the very last one. And then we're going to have everything before that, which is X minus 1, and we're going to have failures. All right? And this is for X equals 1, 2, etc. On and on. To infinity and beyond. All right. Recall for the binomial, X could be 0, because I could have, if I do a fixed number of trials, I could have no successes. But here, I'm going to have one success. And then X is going to be what trial that success was on. All right, so let's do an example. Okay, so let's say we have a door-to-door salesman. All right, and the probability he goes door to door, the probability that he makes a sale at any given door is 0.15. Right, so 15% of the doors that he visits, he makes a sale. And let's assume that, the sales are independent. Meaning if he goes to one door and he makes a sale, and then he goes to the next door, that the fact that he made a sale at one door, that has no effect on whether he's going to make a sale at the next door. All right. And he decides that he needs to make a sale. So he is going to visit today. He's going to visit houses until he makes a sale. And then he's going to stop. Okay. So we're going to let X be the number of houses he visits. Until he makes a sale. All right, so according to our definition, X has the geometric distribution with parameter P, which here is 0.15. All right, here's the question. What's the probability that he makes a sale on the first house? Well, it's the probability he makes a sale on any house. It's 0.15. This is going to be 0.15, but that happens to be P of 1. Okay? So P of 1 in general is going to be just P. So here's 0.15. And that fits in with my rule up here, all right, because Q, because it would be P of 1 equals P times Q to the 1 minus 1, all right, and Q to the 0, which is what that is 1, all right, so P of 1 equals P. All right, what's the probability that he makes a sale? First sale. On the second house. All right. And this is P of 2. And so if he had made one on his first house, he would never get to 2, right? So he'd have to they'd have to have a failure at the first house, and then a success. Right? So P of 2 it's P times Q to the 1, which is PQ. That's not Q. Oops. Sorry about that. All right, PQ, so that is going to be 0.15 times 0.85. That's Q, so P is 0.15, Q is 1 minus. So 85% of the time he doesn't make a sale at a given house. All right, and if I multiply that together, that gives me 0.1275. What's the probability that he makes his first sale on the 6th house? So P of 6, this is going to give a probability of having 5 failures and a success. Right? So by a rule, this is going to be P times Q to the 5th. So I've got my 1 success and 5 failures. For this, it's going to be 0.15 times 0.85. I'm going to take that guy to the 5th power. This happens to equal 0.067. All right, so what's the probability? Here's one that he visits 6 or fewer houses. All right. For this one, to do this, I mean, basically this is P of 1 plus P of 2 plus plus P of 6. All right. Now I could calculate these. I could say, okay, this is PQ, this is or this is P, PQ, PQ squared, etc., etc. All right. But there's a rule for it, so I'm going to teach you that rule. All right, so this is what I will. All right, so if X, it has the geometric distribution. Let's find our P. Okay. Then the cumulative distribution function. Let me call this the CDF. All right. Is capital F of X. Again, this is the probability that X is less than or equal to X. If this is 1 minus Q to the X. All right. Just to verify it, let's just verify it for X equals 2. All right. So F of 2 is the probability that our first sale is on the first or second house. Okay. All right, so P plus 1, go up here. P of 1 is 0.15, P of 2 is 0.1275. Okay, so that's going to be 0.2775. Now if I use my rule, this is going to be, according to my rule, F of 2 should be 1 minus Q squared. So that's 1 minus 0.85 squared. We got 1 minus 0.85 squared, And that equals 0.2775, same number. All right. So the question we had asked that I said I didn't want to add up all those 6 things is the probability that he visits 6 or fewer houses. So the probability that he visits 6 or fewer houses is that the number of houses he visits is less than or equal to 6. This is the same as f of 6, so this is 1 minus q to the 6. This is 1 minus 0.85 to the 6. 1 minus 0.85 to the 6 equals 0.6229. All right, so there's a 62% chance that he'll be done after 6 houses. All right, so let's answer another question. What's the probability that he visits at least 11 houses? All right, so this is the probability that x is greater than or equal to 11. All right, so I have a rule for less than or equal to, but I don't have a rule for greater than or equal to. So what I need to do is use the complement rule to come up with another way to say this. All right, so the complement of x is greater than or equal to 11 is the probability that x is less than 11. And then to make this less than or equal to, that's the probability of being less than or equal to. So if it's less than 11, the biggest it can be is 10. Right, so this is 1 minus f of 10. And f of 10, by our rule, is 1 minus q to the 10th. All right, so that's going to give me 1 minus 1 is going to give me 0. 1 minus a negative q to the 10th. This is going to just be q to the 10th. So the probability that x is at least, or the probability that capital X is at least some number is q to that number. All right, so this is going to be q. This is 0.85 to the 10th. 0.85 to the 10th is 0.1969. Okay, so there's almost a 20% chance that he will visit at least 11 houses. All right, so let's say I wanted to know, on average, what happens. So on average, how many houses will he visit? All right, so I need another rule. All right, so if x has a geometric distribution with parameter p, then the mean of x is mu is 1 over p. So here, on average, how many will you visit? The mu would be equal to 1 over p, which was 0.15. And this is 6.6667, however many decimal places you want, houses. So on average, you'd have to visit somewhere between 6 and 7 houses in order to make a sale. All right, so what about the standard deviation? All right, the mean is this, and the standard deviation of x sigma, this is equal to the square root of q divided by p. Okay, so this is the square root for this guy, for my example. Okay, we'll call this question B. All right. So what is the standard deviation of the number of houses he visits? All right. So sigma for this, for the geometric distribution, is the square root of q over p. So this is the square root of 0.85 divided by 0.15. So 0.85 root divided by 0.15. That is 6.1464 houses. All right, so let's see, according to the empirical rule, 95% of observations should be within 2 standard deviations of the mean. So let's find out what is the probability that the number of houses that he visits is within 2 standard deviations of the mean. We expect this to be at least 90%. All right, so we'll start, we'll have mu minus 2 sigma, mu plus 2 sigma. Okay. Mu was 1 over p, that was 6.6667. I'm going to subtract 2 standard deviations, that's 6.14. This will be the same except plus. Six point 6667 minus 2 times 6.1464, that gives me minus 5.6261. Add them, 6.667 plus 2 times 6.1464, and that gives me 18.9595. Okay. All right, so we would say, so when I look at my, my possible values, I got 0, it's not possible that way. Just drawing another line. 1, 2, 3, 4, 17, 18, 19, right? And here I'll have negative 1, negative 2. All right. So according to this interval, we expect by the empirical rule that x should be within like negative 5.6 to 18.95. So we think, at least 90% is in this range. Right. So So what actual values of x occurs in that? Well, the x is anything greater than 1 and on. Right? So that would be between 1 and 18. Right? So the probability that x is between 1 and 18, right? That is f of 18. And that is 1 minus q to the 18th is 1 minus 0.85 to the 18th. 1 minus 0.85 to the 18th equals 0.9464. Which is indeed over 90%. Okay. So 95% of the time he would visit anywhere between, or over 90% of the time he would visit between 1 and 18 houses. So that is consistent with the empirical rule. All right, so that's all I have to talk about the geometric distribution, and until next time.